Let's resume what we did last time. We require this dh over d lambda, this derivative. And now we could perhaps simplify this equation by taking the opposite of this derivative in the denominator of this ratio, so d lambda over dh. Since lambda is a function of h, we can actually calculate this derivative. So this is now the derivative of d lambda over dh that we need here in the denominator of this fraction. Okay, and we calculated this. I was a little bit clumsy here. I put the wrong equation here, so I required really the derivative, not the function itself, not the lambda itself. And we found this derivative that now fits in here. So I have dn over dh, and dn of the a over dh I need it here to calculate this d lambda of dh over here. So this dn over dh, I have it here multiplied by this fraction. So let's now calculate the overall d lambda over dh. This is minus sign here, lambda 0 in vacuum free space, n squared of h times the result I have here, delta n. I have e to the minus h over capital H times minus 1 over this capital H here. Let's try to rewrite now all this in this equation here. This lambda is a function of course, of kind of function of h. Lambda of h. Also here I could write it lambda of h. You know that lambda changes with frequency. And in the denominator, minus sign and minus sign cancels out. I have lambda 0 over n squared of h. Delta n I have here, delta n. I have e to the minus h over capital H. I have 1 over capital H. Now, what can I do here? This derivation was exact here, exactly with the same similar triangles with the same angle here. All triangles have the same angle here. Same angles everywhere. So these triangles are similar between them, among them, the triangles. So with similar triangles, this was an exact derivation what we did here. But now let's see what's really important here. What is really important in this equation? Lambda, yes, it changed, the wavelength changes with the height, the altitude. But as we go higher and higher, it gets closer and closer to lambda 0. So for our accuracy, we don't even know what h is in the parametric equation. We don't know what delta n is exactly. It changes over. You saw that from the map that delta n over the world changes by as much as plus minus 15%, plus minus 20%. So this changes much. This is this age, the barometric age, also changes with the time. In winter is smaller, in spring, in summer is a larger number. So both these we are quite inaccurate. So now if I make a mistake of 1% here, I can simply assume that lambda of h is approximately lambda in vacuum. And this means that maybe I can cancel out this lambda of h with this lambda 0. Further, the refraction index is also very close to unity. So also for the refraction index, n of h, this is very close to unity. Now, because the final result will not change much if I put unity here. So I can simply cancel out this one here. What I'm now left with, I can write it here, an approximate equation, because I made approximations now. I have, this is double fraction, so h is in the numerator. In the denominator, I have delta n. I'm left with delta n in the denominator. And I have here exponent function. Because it's in the denominator, in the numerator, I should remove the minus h over h. So I have quite a simple equation now that this radius here is now, radius of course is a function of the altitude where I am. It's a function of h, of the altitude. This radius is here now capital H, so barometric constant, divided by delta n times here e to the h over h. Let's try to calculate now this. How much is this? Here I have an overall year average is 8.5 kilometers here. Delta n, the average value is 0.0003 for radio. For for light, it will be half that value of delta n. But this thing now divided is now, this is 3 times 10 to the minus 4. 8.5 kilometers times 10 to the 4th power is 85,000 kilometers. 85,000 divided by 3, I get 2. I am left with 1. 3 into, I'm left with 2 and left with 2. 3 into 25 goes 8 times. I am left with 1. And now I have 10. 3 into 10 goes 3 times 3 kilometers. Times, of course, this exponent function, which is equal to 1 at sea level. This exponent function, oh, sorry, again I made the same mistake, is equal to 1, so exponent function of altitude over barometric constant. And this is our result. Simplified, of course, so I have to write here the approximate sign. But for our accuracy, with delta n, with h, n of h, we make an error that is less than 0.1%. Here we may make 20% error. Here we make between winter and summer, we may make up to 10% error. So these errors here and here are much smaller than this here. So what does that mean? Radio waves do not go in straight line. Radio waves follow a curvature radius that at least as altitude above sea level goes to 0, then this radio is approximately 28,333 kilometers. This is dry only. Only for the dry part of the atmosphere. Of course, the whole formula tells a little bit more. So this I should call that this curvature is actually the dry curvature. I could put the suffix dry here, because we calculated everything for the dry part, are dry. What happens if we have two curvatures? Here, out of here, I get from this term here, I get the R dry, that is equal to H dry over delta N dry times the exponent function H over H dry. This is this curvature, and the curvature for the wet part of the atmosphere is now H wet over delta N wet part, exponent function e to the minus H over H wet. How to sum curvatures? Curvatures actually sum the opposite values. So if I have curvature radius, then curvature is actually 1 over r is the curvature. And curvatures do sum here because both effects actually bend the ray in the same direction. So it's 1 over the curvature of the dry part plus 1 over the curvature of the wet part. Now, how much is the whole curvature radius here? Is of course smaller than this one and smaller than this one. If we curvatures are opposite values of curvature radius. Maybe I think you learned this at math in the second year. That curvatures are the opposite values of curvature radii. And what now becomes r? This thing here is about, so the wet part, now don't take this word for very accurate. This part, the wet part, is usually 10% of the dry part. 10% in normal weather at normal latitudes with some reasonable temperatures in spring or in fall. Not in summer, not in winter, not at the equator, not at the South Pole. Okay, this is the order of magnitude. This here is around 10%. So this curvature of the whole curvature, including both dry and wet part, is approximately 1 over 25,000 kilometers. So this 25,000 is less than the dry part itself is 28,000. Around 10% down. Very approximately, because there are many things that change, especially the wet part changes very quickly with temperature, especially with temperature changes. Now, the wet part is very small in winter, and you are used to see clouds in winter. But what you see in clouds, you see ice crystals and see water drops. What we are talking here is water vapor. There is not much water vapor in winter. There is lots of clouds, but not much water vapor. It's mainly drops or ice crystals, so snowflakes. That's what people maybe don't understand, why winter is dry and summer is wet, actually. Summer is wet because the saturated pressure of water vapor in air increases very quickly with temperature. The warmer the air, the more water vapor it can take. And here we are only interested in absolute values of humidity, not relative values. Remember that the weather guys on TV only talk about relative humidity. We are not interested in relative humidity. We are interested in the total humidity that's in the air, total water vapor. That's the difference. So we have to calculate our things with this R dry should be here, or this R will be in the range of 25,000 kilometers. 25,000 kilometers is a very large value. What does that mean in the case of the Earth? Our approximation for the Earth is that the Earth is actually a sphere. A sphere with a radius of around slightly less than 6,400 kilometers. So this radius of the sphere, radius of the Earth, is here approximately 6,378 kilometers. And this is very approximately. More accurately, we should model the Earth as an oblate ellipsoid, and we should have the equatorial radius that's larger by 21 kilometers than the polar radius. But we are only taking the equatorial radius here for our approximation of the Earth. What does that mean for the radio wave? If I have a mountain over here and a mountain over here, the radio waves now follows not a straight line, but follows a curved radius. And actually all, even if these two sides are not visible directly among them. So if I draw the straight line here from one transmitter to the receiver, even if there is no geometrical visibility, there may be a radio visibility. Because this radio ray actually follows a segment of a circle with a radius r. It is not a straight line. Even an optical ray, it is not a straight line. But for the optical ray, this constant is different, it's smaller. So the optical ray will actually take a path somewhere else. So if I redraw this detail down here, what I want to say. If I have two sides with antennas, the geometrical visibility is a straight line. But the geometrical visibility is not the optical visibility. The radio visibility is a curved line with one radius. So radio. And we have yet another line for the optical ray. If we have, say, a laser on one mountain top and we are watching it on the next one. So this is optics. Optical, where radio has an R of approximately 25,000 kilometers. But optical is 10 times more. It's less curved, so its curvature is smaller, its radius is larger. Optical has a radius of about 50,000 kilometers. You see that when you want to measure things accurately, optical rays are actually not straight. Even with such smaller wavelengths like optics, that small change in the refraction index is actually curving our optical rays. There is no straight line. So what I mean with that? You usually take your girlfriend to watch the sunset. That's the usual way you do. True? When does the sunset happen? If you have your girl on the mountaintop and watching the sun setting below the horizon. What happens over there? You are actually not watching the sunset. This is the Earth, I redraw the Earth here. Here is you and your girlfriend watching the sunset, but what you actually see from the sun. As long as we are in vacuum, rays from the sun are straight. But when they get into our atmosphere, they actually curve down to the observer. So when we see the sun on the horizon, the sun has already set. We are just seeing it because of the refraction in the troposphere. And there is a center angle about 1 degree. So the sun has already said the sun is half a degree across. There's about a 1 degree difference when you see the sun, and the sun geometrically has already set below the horizon. And even more is in radio. In radio, you can receive signals from satellites that already set below the horizon. Even much more because there is more tropospheric refraction for radio rays than it is for more tropospheric refraction for radio rays than you have for light. light, the R is larger, refraction is smaller. Delta n for light is half of delta n for radio. How to calculate all these things? How to calculate such radio links as I have depicted here. Now it again makes sense to calculate things using curvatures. And we introduce a new quantity called the effective radius of Earth. R effective radius. 1 over R, the curvature of this, the effective curvature is the actual curvature of the Earth minus the curvature of our ray. So these two curvatures actually subtract. You see that they work one against another. So the curved Earth would actually obscure our receiver, but the ray avoids the Earth curvature. And because of this avoidance, we have this question, this minus sign here. What is now this effective radius? Of course, this effective radius, this one is fixed for approximation, but this one depends on the height above sea level. This is a function. So also this R effective radius of the Earth will be a function of the height. At what height is our radio link or observation of the sunset from the mountaintop actually done? And we are I'm just noting now this effective radius for the sea level, for h is equal to 0. For h is equal to 0, this thing here becomes around 8,500 or 8,600 kilometers for radio. 500 of 600 now, I don't know the exact figure, it also changes. But it's 7 kilometers. But it's 7,300 kilometers for optics. It is no longer the 6,000 kilometers of the Earth. Now, what we want to see is if we have a tower of a certain height, what is the range of the tower, from the top of the tower? How far can we see from that tower? If I redraw this picture, maybe this is good enough, but I have to redraw this detail up here. If I have just one tower here, I'm erasing this, not to having to redraw the whole picture, the whole Earth again. This is true R of the Earth, but that true R is valid for a straight line for geometrical visibility. So geometrical visibility, I can draw a triangle here that has an R Earth here. This is also, this part is R of the Earth, and this is the height above sea level of my transmitter. And here I have the distance, my coverage of my transmitter, my visibility, geometrical visibility. Geometrical visibility. And let's now try to solve now the Pythagoras here, over here. So the Pythagoras says h plus re, this is this side of the triangle here, squared is equal to d squared plus here plus r of the Earth squared. I'll just erase this to make more space here. So if I work out the right side, this is h squared plus 2hr of the Earth plus here r Earth squared. Now r Earth squared mathematically cancels out. So therefore the range of our transmitter on a tower of a height h now is d is square root of h squared plus 2hr Earth. Okay, but what we are really able to do? What we are really able to do is make towers that are much smaller than the radius of the Earth. At least 1,000 times if you go to the top of Burj Al Arab in the Emirates. Or the Babylonian Tower. Those people were always interested in building tall towers, even from the Babylonian age. So h is much, much smaller than RE. What does that mean? That d is approximately square root of 2hr of the Earth. What happens now if I have, say, a tower? If we make an example that r of the Earth is 6378 kilometers, and we have a tower that has a height of 100 meters, that's 0.1 kilometer. Let's try to find the distance here, the range of our transmitter, the geometrical visibility. The geometrical, should use capital Earth here. Use capital Earth here. So it's 2 times 0.01 times 6378 kilometers squared, kilometers. I expressed all quantities in kilometers, so it's kilometers squared. So I'll also get the result in kilometers. This is now square root of 2,000 twice 6,000 is 12,000, so it's 12. 378 is 600, 700, 700, and 78 times 2 is 156. So is 5.6. The unit is kilometers here. And if I take this square root, now I don't have a calculator over here. Oh, maybe I could use my computer if the calculator works here. If the calculator works on my computer. So let's try it now. So 1275.6 square root. Square root is 35.7 kilometers. Oh, where is the green marker here? 35.7 kilometers. But this is geometrical. With no refraction elsewhere. Now let's try to look what happens with radio. I use the same formula, I just plug a different value for the radius of the Earth. So it's 2 times 0.1 times 8600 kilometers squared. So this thing is now 16,000, 70,200. So 70. Yes, and this is, if I take the square root, it's already kilometers out. And I calculate this range right now. Calculating this, so 1720. 1720. Where is the square root? Square root is here. Is 41.5 kilometers. 41.5 kilometers. I get with radio. So radio visibility is slightly larger than the radio visibility is slightly larger than geometrical, and optical will be somewhere in between. So if I draw here optical, I try now with D is twice 0.1. That's my tower size or observer height, 7300 kilometers squared. This is now square root of 73 is square root of 1, 4, 6, 0. Outside the square root is kilometers, and now we take the square root, 1460, just to avoid guessing, is 38.2 kilometers. So even in optical, we get much farther than geometrical. So even here there's a difference. If we calculate things, and the simplest way to do is just to use this effective radius. So we put inside here not the radius of the Earth, but we put here the effective radius, considering also the refraction in the troposphere. So we get much further away. What we could say about the Earth itself? With 1 bar pressure, I have this radius, 25,000 kilometers. This is with 1 bar pressure. If I had here a much larger pressure than 1 bar, I could obtain a larger curvature, a smaller radius. If the Earth's atmosphere would go up to 4 bar pressure, approximately 4 bar pressure of air, the radio wave could actually track the Earth's surface. The curvature of the radio wave would be the same as the curvature of the surface of the Earth. So this would give me here an infinite effective radius of the Earth. So flat Earth. I could flatten the Earth. Well, now it's a little bit difficult to increase the air pressure all over the Earth at 4 bar. You have to really find lots of gas. But there are things that actually happen. Where in space does this happen? Where the radio waves actually can track or even curve more than is the curvature of the planet. Venus has an atmosphere that has 94 bar of pressure, almost 100 bar. On Venus, you can actually not see the horizon because you see over the horizon. You go with your sight all over Venus and around, except for the haze of the atmosphere on Earth, on Venus. But on Venus, actually, you can make radio contacts anywhere you want. From the surface on the Venus to another point of the surface, the only problem is that this 100 bar of CO2 that's heated almost to 500 degrees centigrade, your radio will melt. It's very hot on Venus. That's very hot. So there is yet another issue here that we just another constant that is used in propagation software, and I have to explain you this additional measurement, this additional unit, and it has an unfortunate letter K. We usually use K for the wave vector. Here it is not the the wave vector. This is the unit K, and is written as a capital K, is now the effective radius of the Earth divided by the true radius of the Earth. For this case here, for this calculation we made for radio, this K is around 4/3. So this ratio K actually tells you by how much does the effective radius actually increase. Air effective is now approximately this K times the real radius of the Earth. And we are making our calculations. We put 4/3 here. This is about 4/3 for the normal atmosphere we were talking about here. This ratio here is 4/3. If we are particularly careful about our radio links, we should actually place here smaller value. So if we are really careful about the radio links, we use a K of 1, not 4/3, but 1. 4/3 is the average value, but in particularly unfortunate conditions for radio wave propagation, we also plug in smaller values for K, not 4/3. K is a capital letter. Okay, we had before we had the capital N. You remember the capital N was our delta N was actually now capital N times 10 to the -6. This is a special unit. This is unitless, but it's a special quantity in radio propagation software. And this K is also a special quantity, just to remind you about these two questions, these two quantities. They were just introduced to simplify our calculation. We say that the radius of the Earth for radio waves actually increases by 4/3, approximately 4/3. Now, things are not that simple, as plotted here. I have to finish this discussion with one special case. This is all true. All we derived here is true for a well-mixed atmosphere. So an atmosphere where you have lots of vertical flowing of air, both up and down. And in a well-mixed atmosphere, the well-mixed atmosphere really tracks the barometric equation. The barometric equation is not true in certain special cases that are quite frequent here in Ljubljana. Well, in Ljubljana we call it fog, but it is not the fog the problem. The problem is the cold air that accumulates in a valley, in a closed valley. So if I draw the sea level here, the Earth is curved, so I draw a sea level here. I draw the actual sea surface that may include mountains, that may include flat valleys, and the mountain on the other end. What now may happen in certain meteorological conditions? It may happen that I have so-called inversion. I have a temperature inversion of still cold air in my closed mountain valley. So I have cold air. And I have warm air on top of it. What happens now in this case? So if I try to draw here the temperature with altitude, so this is temperature, this is now, this is altitude. Altitude is h here. I draw temperature here. What happens with temperature? Temperature is low up to the end of the inversion layer, and then it springs up to a higher value, and then again starts dropping. Temperature should be dropping all the way. In a well-mixed atmosphere, temperature is dropping all the way as you increase. It drops about 2 degrees centigrade per 300 meters per 100 feet, so it's a constant. But in the case of temperature inversion, which is frequent in closed valleys and with still air with no winds, we get for temperature, we get this. What do we get for the refraction index? The refraction index also drops with altitude. I will draw with the green line, I will draw the refraction index. But as the air gets warmer, it makes a further drop here. So this is now the curve for my refraction index, N of H. This was temperature of H. What may happen now for my radio link? Before I had a radio link between two mountain tops with microwave directional link with directional antennas, and this link was following this track here, going partially through the inversion layer and ending up in the ender antenna. Now what I get on the inversion layer, I have a jump here of the refraction index. In a larger refraction index, I get refraction down here. I may no longer have a direct visibility on this link. I no longer have visibility because of this refraction of the inversion layer. So the attenuation of this link is going to grow. It is not going really to drop to 0, but it is going to increase. The attenuation is going to increase. In the practical experiment, I have a link that's it's 90 kilometers long from Kobaryshki Stow to Krim. Goes over Ljubljana here. And in certain meteorological conditions, that link, when I have fog in Ljubljana, that link drops down by 20 dB. I measure, all of the time I have telemetry, I measure the signal level on this link. And this is a real problem. It was a problem also for our broadcaster. They had a link from Nanos to Krvavec, and that link was also dropping down where there was fog in Ljubljana. There is yet another problem. If these two stations were, say, A, B, this link from A to B drops down. But I may have some smaller obstacles here, and I may have stations C and D here. These two stations, C and D, usually don't hear each other. There is no link between these two stations. But in the case of the inversion, I may get here total reflection. This was a refraction here. Up here was a refraction. I made a total reflection. So in the case of this inversion layer, I may get a contact between C and D that before had no visibility. They had no visibility before, and now I have a radio link. That is usually probably interference. Because C and D could have used the same frequencies in stationary weather with well-mixed atmosphere. This is no longer true in the case of the inversion layer. So many such things happens, and this cannot be, the temperature inversion layer can hardly be predicted by software because weather is unpredictable. This maybe happens here in the Ljubljana Valley over a distance of, say, 30 kilometers. On the sea, this thing may happen even on much larger distances. On the sea, you may have inversion layers. On the Baltic Sea, you may have inversion layers that extends for 1,000 kilometers. So actually, you get interference in Poland when there is someone transmitting in the United Kingdom. All over the Baltic Sea and the Northern Sea, you may have this effect. The longest such effect, I think it was observed in practice, the longest effect of total reflection on the inversion layer and bouncing many times, because now we have actually a dielectric, we have an optical fiber for radio waves now that builds inside the inversion layer. There were reported links between Hawaii and California. Between Hawaii and California, you have 3,000 kilometers of ocean. You may have an inversion layer extending for 3,000 kilometers over the Pacific Ocean. Oh, even this happens. So this is really unpredictable. What we are trying to do, otherwise, we are trying to predict something with some software. And I'm also only using now some 10 minutes of this hour just to show you some of the software here. Maybe first to show you the map I gave around. So if we can turn the projector on, I will lower the screen. I still have to plug in the cable. Okay, we have screen now. So I will try first to show you the map I promised you the hour before, just to show you the map of the world map. This should be the right one. Hope it is. So here you see the world map. I sent this picture around the hour before. You see the value of n. We had it behind here. The value of n goes below 300, the index difference below 300 in the Sahara Desert. Also close to 300, or even below 300 over Antarctica. Antarctica is very cold, so we have very low delta n because there is no water vapor. Here, there is no water vapor, but the air is very hot here. Also, very hot air on the Sahara Desert also has a lower refraction index because it's more rarefied. On the other hand, in the equatorial regions, we have very high values of n that extend from the tropical ocean, that extend here in the Amazon desert, that extend into Indonesia, Maldives, Indonesia, and so on. We have very high values of n. And this is a world map. You see also for the North Pole, but it's not, the North Pole is not as cold as the South Pole, so also n stays a little bit larger. In our moderate climate areas, you see that we have slightly above 300, say most of Europe is slightly above 300. American West is very dry, 280. No water vapor over there. So this is just to show the map so that everyone can see it here. Further, we will have a look at the software. I sent you just what it is, how it works. Also, let's try to turn this thing off. Okay. So let's try to just like to show some. There is lots of propagation software. None is very good. This is a very old one I have here. It's RadioMobile, because it's French. It's a Canadian that wrote it. Working with Canadians, you'll better do to learn French if you have anything to do with Canadians. I'm trying to find it now where I have it, my disk here. RadioMobile wireless, I think it was called initially. Let's try to an example here. So let's try to run it. Hope this is the correct version. Okay, now we have the software. So in this software, what we can do here? We have to insert a map first thing. For this software, you have the desktop version like this one here. This is the old one. And you have also an online version that's available right now also on the internet, but I don't have internet access here. So what do I have here? The problem is I don't see the cursor right now. Okay. Also, this should I put it here? First thing, I should actually insert a map up here. Did I press the right one? No. That's wrong. No. It's a problem. It's just I don't see to the screen. So. Because those icons are so small that I don't see it here from my position. I have to move my computer over here. So what this software does, it actually uses the actual digital map. Uses the actual digital map. And here I have to insert the first, where is the cursor right now? Here. Do we have it here? Okay. So first I have to insert the map, and I have to put a new map here. Using here open map, but I remember 25 years ago it was quite difficult to find good maps because internet was not working okay, they were not available. Now they are available maps, and now you can the software itself is able to download this map from the internet. Then you have to set up your networks. Then you have to set up first your stations. Unit, that are called unit properties. Unit properties here. Unit properties. One down here. No, where is it gone? Oh, it's on this screen here. It ended up here. It all ends up on the screen I have right here. So this is quite unfortunate. It all ends up here. So. For unit properties, you put in your locations. They have names, like Thurstel is a mountain, and you put in the coordinates, and it is able to look at its own map inside it has. So enter latitude and longitude, like here. You can enter it here. Oh, it's again on the other. All these sub-windows appear on the other screen. We have to put longitude and latitude. He will open his own map. So I say if these things are correct, here now, if these values are correct, I hope they are correct. He will show me a small map he has. I say, OK. And now the other map is also appears somewhere, but now I no longer have it here. So I could, he calculates automatically the elevation above sea level. The elevation above sea level is calculated automatically. And then I can see, when I have this thing set up, I can set up the networks. Networks are here. So networks are open networks. Open networks is second line. Open networks is here. And I will say I will open this network here. I already inserted networks. Also, if I edit networks, for each network, so let's say open networks now. Open networks, I will put in which is here, say, this one up here, this one. This one should be the one I want to show you some example here. OK. And now he drew me this network. It has some membership, but all the links between the members are drawn. All the links that do work, they are drawn green. The links that have no visibility are drawn red for the networks. Let me say. And now let's find out now Sorry, I hope I have F2 is the link. Maybe F2 works here. F2. Oh, now I have the little map here. You see the little map also shows me the surrounding of this. This little map shows me the nearby peaks. You see that the mountain peak was the tallest here, and the nearby peaks are here. And now I can check these links. I can draw a profile of this link, and I check it here. So he is going to draw the first 3 Fresnel ellipsoids. For this link, this is a link that has good visibility from Trstel to Svetogora. This is the western part of Slovenia here, the western part. I have the map here. You see that this link is green because it has good visibility. But this is not necessarily true if I try some other link. If I try a link from, I don't see the cursor. Okay. Okay. Let's try here now Černá-Prst. Yes, it's the third one. The third entry here. And now you see that this link is actually painted red. He says that this link has no visibility at all. Yes, this link has a problem because it has Tarnowski Ghost in between, the peaks of Tarnowski Ghost. But his map is not particularly accurate. You see that this altitude of Černá-Prst, it's actually the tallest peak, but the map is not particularly accurate. What can I do in this case? I can put here the real altitude in the unit properties, or I could raise up my antenna. I can increase here the antenna height to see what happens. I will increase the antenna height, so I go down here, and I increase the antenna height here. So I can try with putting an antenna on a taller mast if the mountain is not that tall, and I go up here. So if I put it further up, now we are still at 20 meters. I'm not pressing the right thing because I don't see anything. Please put this away. If we can put it a little bit higher. Does it change? Yes, it did change something. And the signal should be raising right now. I should put it over 50 meters high here because the map is not particularly accurate. So I can try such things to see what happens in the real radio link. What height did we reach right now? 50 meters, 50 meters. Now the signal is already rising. Maybe I can try the same on the other end of the link. I can try the same here. Also raise this antenna. Also this altitude here is not particularly accurate. We can do something. Taller antenna. We already have gained now with taller antennas. We can gain some 10 dB. If we can go further higher, you will see that this obstacle will actually let our signal go up. And this link, I can tell you, this is not now an imaginary link here. This is a real link I have in the mountains. And this link actually works. So this simulation sees, you see that it's changing color now. it became green. The link is green now with a much taller antenna. Now it's 58 meters. It's not the tower height, but the map is not accurate, the map on this side. That's the reason why I had to raise the antennas to get into real condition. This link actually works. Though here the tops of the Tarnowski ghost just enter into the first Fresnel zone. Yeah, I have some attenuation, but still this link works. So this could be checked. This is something interesting to play. I have other options. You can calculate the radio coverage from a certain point and so on. The problem with this software, it's a little bit old. This graphics is from 30 years ago, is Visual Basic from 30 years ago. Zooming this map is a headache. Just to tell you where is the problem with using such old software. But this is available free on the internet. You can freely download the maps. You have also an online version that has newer maps, much better maps. But the online version is no longer free. You can only calculate links for amateur radio frequencies, not for any other frequencies, so professionals cannot use it. The software itself is based on, again, on an old work of the US government. They made not just assemble the theory, they also assembled theory and data from experiments, from experimental links, because this guy here is also has the map also includes terrain coverage. So he knows whether the terrain is flat terrain, whether it's just grass there, whether there are buildings, it's a build-up area, or whether there are pine trees, which are good absorbers. He knows these things and he calculates this thing out from experimental data. So that's the reason why this program is still useful even today. Just to show you, and maybe it's better you play at home because we already used a quarter hour just to show you this program here. And we have to proceed with the midterm exam.